So let's go back now to our 4 scenarios and identify how is the energy stored for, moment B in all of these different situations. So what do you think here?
Gravitational potential?
Okay, gravitational potential, and you can kind of do a checklist. You can ask yourself, are 2 masses separated? Yes, this is separated from the Earth. It could fall. Is it moving?
No.
No, so no kinetic. Is something stretched or compressed that wants to go back to a relaxed position?
No.
No. Have I done anything to make the molecules inside the air or the object move faster?
Well, not really.
No.
Now here's an interesting one. Are the molecules moving in there?
Yes.
Probably.
They are, right? It's not an absolute 0. So as long as it's above absolute 0, the molecules are moving. So it has internal energy. But rather than always account for these internal energy things start with, we're just going to say that's our 0 level of internal energy. So you don't need to ever consider the internal energy things start with. We'll just look at how they change over the process. Okay, so none of those other types. So all we have is gravitational potential. So the entire pie, this is a pie chart. The entire pie here is EG. It's all stored as gravitational potential at that moment in time. Okay, the car. And on the diagram for the car, do you see that the surface under the car changes at B?
Yeah.
So to simplify things, I'm going to say
not
there's no
supposed to.
friction while I'm pushing it. The friction starts after I let go. So at B, do we have gravitational potential energy?
No.
No, because it's not raised up. Okay. The same thing is true with gravitational potential energy, though, as with internal energy. In a problem, you could just decide, if you're doing your entire situation on the table, you could just say, okay, that's my ground level, and I'm going to consider that to be my 0 level of height. Oh, the computer went off. So you can adjust your 0 level of gravitational potential energy. Okay, so for B, at moment B, what kind of modes do we have energy stored as? We said no gravitational
Is it
potential.
kinetic?
Yeah, it's
We have
kinetic.
kinetic. Elastic potential?
No.
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 Because nothing is been stretched. If it was the kind of car where you had to wind it up,
Well, it is actually.
it is.
But in the
I
example, we
wind
didn't
it up.
have that.
Yeah, if you wind it up, then you would have to account for that. And no internal energy, because we haven't done anything to it to make those molecules move faster. So this is going to be entirely kinetic energy. Okay, the bow and arrow. Now in the bow and arrow problem, we're going to have the ground be our 0 height. So at B, do we have gravitational potential energy?
Yes.
Yes, we
I
do.
suppose so, but we can neglect it.
Nope.
Oh, really?
No, we can't neglect it because part of the process is to change height.
Oh, I thought we were just looking at B.
We're eventually going to look at all of them. So we're going to have the whole process eventually. So we do have gravitational potential. What about kinetic?
No.
No, it's not moving yet. It's just been squeezed.
Oh, wait. Now we're
What
not
What
looking
about
at
elastic
all of them?
potential?
Although
Yes.
if you're pulling back a bow, you want to be moving the L backwards.
Oh, that is a great question. And that's going to come up again and again. Because that's similar to here, right?
Yeah.
I had to move it to get it from here to here. So in that process, I had to speed it up, and then I had to slow it down. So at this point,
Okay.
it's at rest again. Yeah. And usually we'll simplify that by saying, okay, well, we moved it at a constant velocity. And it instantaneously stopped. Okay, so here we have gravitational and what else?
Elastic.
Elastic potential. And we haven't done anything to the molecules inside the object. So,
Oh, it doesn't have kinetic?
what?
It doesn't have kinetic?
No, because it's not moving yet. See, look,
But the height hasn't changed yet either.
the height hasn't changed yet. So
So,
what I did was I took the arrow, I pushed it in. So here's moment B. Snapshot B, nothing is moving
but it has gravitational energy?
because it's above the ground.
That's a bit
So, but
hard to define, I suppose.
What?
That's a bit hard to define.
That it's above the ground?
Well, I mean, yeah, I suppose so. Because the ground could just be the bottom of the bow where it's
it
resting.
could. Okay, so that's a great idea. So you could make this 0.
Yeah, basically.
If you do that, you're later going to have negative energies, which are a little bit weird to think about. Because at this point, it has more energy. How would you say the gravitational potential energy compares here as opposed to when it's on the table?
Well, if we make the bow 0, it'd be more negative.
So if this is the 0 level, now the height is negative, and now it has negative gravitational potential energy, which is kind of hard to conceptualize.
Okay, so
usually what we do is we put the 0 at the lowest point in the problem.
Okay.
So that we can say this is the lowest gravitational potential energy and this is higher.
Just for this class.
What?
Just for this class.
No, always.
Oh, always.
Yeah, everybody will do that. Yeah, usually you put your 0 level at the lowest point of the situation. Because the fact that it could go down there is irrelevant, because in my problem it's only going to go from here to here. So I'm going to set 0 at the table rather than on the floor, because it's not going to go down there.
Oh, and even if we did set 0 at the floor, then theoretically it could fall down a hole and keep
Right.
going down one.
Right. So yeah, if it's going to go in a hole, you'd want to put the bottom of the hole as your 0.
Oh.
The only thing we can actually measure with energy is changes. And so we have to set the 0 level somewhere, and then what we'll really be working with is changes. But it helps us, it makes it easier to work with actual values. So if we set a 0, then we can calculate different values, and then really we're working with the changes though.
Okay.
But great question, and keep asking questions, because there are things in this lesson you're going to struggle with that are going to be like, what? That doesn't seem right. So really struggle with those things and bring them up, and we need to talk about them, because those are the concepts that are important. There's a lot of concepts today. Not really equations, but all the ideas that underlie all of the energy stuff. Okay, so at this point, it's not moving, but it is above the ground. So it has some gravitational potential, and it has some elastic. How much of each? Half and half? I have no idea. So what do you want to do? Half and half, or more of one or the other?
You just get to pick.
Probably more elastic.
Which one do you think it has more of? Just, I
I'm
don't
gonna
even know
guess
the answer.
elastic.
Oh, aren't they kind of going the energies different directions or something? Or do this direction have?
Energy
Wait,
does
does
not have a
energy-
direction.
Okay.
It's a scalar, which makes it really, really nice to work with.
Considering if you aim the bow up and then shoot it, the bow will escape or go up, I suppose. I'm gonna assume that the elastic is stronger.
So let's put more elastic. We
if
don't
that
know.
made any sense.
But here's our pie chart. Some of it is elastic potential, and some of it is gravitational potential. We don't know how much of each.
Well, I think what he was saying is if you
Saying
point
if
it
you go
this way, and the energy is stronger.
Going up.
You're thinking of forces, though.
Oh,
I
You
suppose.
don't really know.
But I guess doesn't the energy affect the force?
yeah, doesn't it?
Or the force? would
They
have
are
the movement?
related, and we'll
Because-
look later at how you can use a force to change the energy in the system. But you have to look at which forces are internal to the system and which ones are external. So we'll do that in a little bit. But for now, we just want to be able to identify what storage modes occur at a moment in time. So this one is gravitational and elastic. Okay, and then what about the cup of hot water? At
Internal.
B. Where's our ground level for the cup of water? The surface
Like
that
the
it's on?
ground.
I suppose so.
Okay. So
There's
no
actually no
gravitational
surface,
potential. What about kinetic? Is the mug of water moving?
No.
No. Elastic? Anything that's stretched? No. Internal energy?
Yeah.
Yes. Okay. So we have a whole bunch of energy stored here as internal energy. Okay, so that was some practice with identifying how is the energy stored in some different situations. Number 4, energy conservation. You remember momentum conservation,
Mm-hmm.
which was the idea that the initial momentum of a system plus any transfers, any changes in the momentum of the system equals what?
The final momentum.
Yeah, the final momentum of the system. We have the same idea for energy. The initial energy of the system plus Any changes in energy to the system is going to be the final energy of the system. Changes in energy are going to be caused by transfers of energy in or out of the system. Okay, that's what goes in number 4, so write that down. I'm going to give you an analogy with money. So you could think of all of your bank accounts, checking, savings, and retirement as your system, right? All your money is your system. And suppose I have 25 cents in each account. So my total system energy or my total system money is 75 cents. Now, if I take money from outside the system, so I get paid at my job, I'm going to put that into my system. So this is a transfer from outside the system coming in. Now what is my total energy of the system?
$1.
$1. Okay, that is a transfer from outside the system. I could also go to the grocery store and buy some food. So I'm going to take money out of my system, and it's now at the grocery store, and now I have less. So transfers can either increase the total money or decrease the total money. Same thing with energy. You can either put energy into your system or take it out of your system. This is why you have to be so careful to define your system and keep in mind what objects are part of your system. Because if the grocery store was part of your system, then when you go to the grocery store, the total system is not changing anymore. Okay, so how you define the system makes a big difference. What we have, the other thing that can happen, you can make transfers actually within the system. So I could say, well, I want to change this from my checking account to my retirement account. Okay, I have different amounts stored in each storage mode, but the total is still the same. And what that would change is, if you were drawing a pie chart, at one moment in time, the pie chart would have half checking, a quarter savings, and a quarter retirement. But next time you draw the pie chart, after you've made this transfer, the size of the pie would stay the same, the same amount of money. But now this one is half, this is a quarter, and this is a quarter. Okay, so internal transfers change the allocation, changes the storage modes. External transfers change the total amount of energy. Changing the total amount of energy has to change the size of that pie circle. Okay, so now we are going to talk about 3 ways that we can transfer energy in or out of a system. Okay, so we're looking here at these external transfers. How can we get energy into or out of the system? So our system, we've got, for energy, we have 4 ways of storing it. How do we get energy into here, and how do we get them out? Okay, and then later we'll talk about the changes between them.